In the silent expanse between galaxies, a darkness waits. It is not the absence of light, but a presence so absolute it swallows even time. The stars scattered across the void seem to lean away from it, as though aware of its hunger. At its edge lies a boundary with no thickness, yet infinite consequence, the event horizon. From the outside, it is a one-way gate into nothingness. From the inside, it may be something far stranger. Beyond that horizon, space-time curves until it folds in on itself. Matter, energy, and the very fabric of reality are drawn inward, falling toward a singularity where the known laws of physics lose their power. To an outside observer, this is the death of a star, the collapse of a massive sun into a point of impossible density. But the mathematics whisper another possibility, that what appears as an end could be the beginning of something new. Imagine the moment of collapse, the implosion not into destruction but into creation. The energy compressed within the singularity surges outward in another frame of reality, expanding, cooling, and giving birth to a cosmos. Galaxies, nebulae, dark matter, and the cosmic background radiation, all the structures and phenomena we know could be the unfolding interior of such a singularity. Our entire universe, with its billions of galaxies and uncountable stars, might exist inside the heart of a black hole that formed in another, older universe. It is a thought that unsettles and beckons at once. If our universe is contained within a black hole, then everything we have ever known is but a chamber in a far greater architecture. And if that is true, then the question is no longer just about where we are, but what lies beyond. The path to this idea began centuries before the first photograph of a black hole, before the first gravitational wave was ever detected. It began in the realm of thought, where mathematics and imagination met. In the late 18th century, Jean Michel in England and Pierre-Simon Laplace in France considered the strange possibility of dark stars' objects so massive, with gravity so strong, that even light could not escape them. It was a concept far ahead of its time, a shadow in Newton's universe, where gravity was a pull between masses and space itself was fixed and absolute. For more than a century, the idea lingered in obscurity. Then, in 1915, Albert Einstein introduced his general theory of relativity, a radical vision in which gravity was not a force, but the bending of space-time itself. The following year, Karl Schwarzschild, serving on the Eastern Front in World War I, solved Einstein's equations for the simplest possible case, a perfectly spherical mass. His solution described a region where space-time curved so steeply that all paths, even those of light, were drawn inward. It was the first precise mathematical portrait of what would one day be called a black hole. At first, these solutions were regarded as mathematical oddities. Surely nature would not allow such extreme distortions of space-time to exist. But the universe is not constrained by our disbelief. Over the decades, evidence began to mount. The work of Subrahmanyan Chandrasekhar in the 1932nd revealed that stars above a certain mass could not support themselves indefinitely. They would collapse under their own gravity once their nuclear fuel was exhausted. For the heaviest stars, this collapse would be unstoppable. Observations followed. In the 1962nd, astronomers detected quasars' brilliant beacons at the centers of distant galaxies, powered by matter spiraling into invisible cores of immense mass. X-ray binaries revealed compact, unseen companions pulling matter from nearby stars. The signs all pointed to one conclusion: black holes were real. With reality confirmed, the mystery deepened. General relativity predicted that at the heart of a black hole lies a singularity, a point where density becomes infinite, and our known laws of physics fail. Around it, the event horizon forms the ultimate boundary. For anything crossing it, return is impossible. The inward path leads only to the singularity. This is where the story of black holes intersects with the story of the universe itself. In the late 20th century, physicists began to notice mathematical parallels between the conditions near a black hole singularity and those at the Big Bang. In both cases, density and curvature reach extreme limits. In both, time and space are stretched and twisted beyond the normal rules. Could it be that what we call the beginning of the universe, the sudden expansion from an incredibly dense state, was itself the interior of a black hole, formed in some larger reality? The thought was not entirely new. Wormhole solutions to Einstein's equations, known as Einstein-Rosen bridges, suggested that a black hole might connect to another region of spacetime. In the 1962nd and 1972nd, the mathematics of Kruskal and Sakaris revealed extended diagrams of black hole spacetime that contained other universes, disconnected from ours, but linked through the black hole's geometry. Most physicists treated these as curiosities, but in the early 2002, cosmologists like Nikodem Popovsky revisited the idea with new tools. Popovsky's black hole cosmology proposed that the collapse of matter into a black hole could be halted, not by a singularity, but by quantum gravitational effects. Instead of crushing matter to a point, these effects could trigger a bounce and outward expansion in a newly formed region of spacetime. To any observers inside, this expansion would look like a Big Bang. If correct, this would mean our universe's own Big Bang was the bounce from a singularity in another, older universe. We would be living entirely inside the interior spacetime of that black hole, the parent universe forever hidden beyond the event horizon. Everything we see, from the most distant galaxy to the faint microwave glow of the cosmic background, would be part of this enclosed domain. The idea is bold, but it rests on real physics, the solutions of general relativity, the mathematics of spacetime curvature, and the questions raised by quantum mechanics at extreme density. It also draws strength from the realization that our current theories cannot fully describe singularities. Somewhere beyond the reach of classical equations, something else must take over. Our understanding of black holes has always been shaped by this interplay of mathematics and observation. Each advance in telescope technology, from radio dishes mapping quasars to X-ray observatories scanning the sky, has revealed more about these objects. And with each revelation, the analogy between black hole interiors and the early universe has grown more compelling. Still, there is a gulf between analogy and reality. To cross it, we must understand what happens to space-time inside a black hole, a realm forever hidden from direct observation. The light from within can never reach us. Our only tools are theory, inference, and the patterns we detect in the universe around us. And yet, that is enough to keep the question alive. The story of black hole discovery is also the story of how the universe began to suspect that its own origins might be written in the same language. From Michel's dark stars to Schwarzschild's wartime equations, from Chandrasekhar's collapse limits to Popovsky's cosmology, each step has brought us closer to the possibility that our cosmos is not the whole of reality, but a chamber within it. The realization struck, not like a sudden flash, but like the slow weight of a truth settling over the mind. It was the kind of truth that unravels assumptions held for centuries, replacing the familiar shape of reality with something vast and unfamiliar. A black hole, once thought to be the ultimate end, might be the birthplace of an entirely new universe. And if that were true, the Big Bang, the moment we imagine as the origin of all things, may not have been the beginning at all. It may have been a continuation, the next breath in a cycle that extends beyond our reach. From the outside, a black hole is finality itself. Its event horizon is the last threshold. Light, matter, and information flow inward, but never out. Space curves toward the singularity as though all paths have been redrawn toward a single destination. To an external observer, time slows near the horizon, objects seeming to freeze and fade as their light is stretched to invisibility. But from the inside, the geometry could be profoundly different. In certain solutions to Einstein's equations, the collapse into a singularity is replaced by an expansion an eruption into a new region of space-time. What appears to be destruction from one perspective is creation from another. This is where the strangeness deepens. Inside the event horizon, the roles of space and time may reverse. Time, as experienced by anything falling inward, becomes a one-way journey toward the singularity. But if that singularity bounces into expansion, the arrow of time could point outward in that new domain. To its inhabitants, there would be no sense of living inside a black hole. Their world would appear boundless, expanding, and self-contained, just as our universe appears to us. The shock lies not only in the possibility itself, but in its consequences for our understanding of reality. If we are inside a black hole, then the cosmos we see, with its billions of galaxies and uncountable stars, is finite in origin, yet without an edge. The greater outside would be forever beyond reach. No signal, no probe, no light from that larger reality could cross the horizon to enter ours. We would be sealed inside, as complete and isolated as a seed within its shell. This model does more than relocate our universe within a larger one. It challenges the uniqueness of our cosmic origin. The Big Bang in this view was not the creation of all space and time, but a local event in a grander continuum. Other black holes in our parent universe could have spawned other universes of their own, each with its own physics, dimensions, and histories. And in our own cosmos, the black holes scattered through galaxies could be doing the same, their singularities opening into realms forever invisible to us. For physicists, the unsettling part is how this reframes the Big Bang problem. Traditionally, the question is, how did the universe emerge from nothing? But if black hole cosmology is correct, the question changes to, what collapsed to form the black hole that became our universe? The nothing of the Big Bang becomes the something of a prior reality, and our own cosmic history is just one chapter in a book with no first page. Such an idea also brushes against the boundaries of physics. General relativity predicts singularities, but it cannot describe them. Quantum mechanics describes the smallest scales, but struggles to reconcile itself with gravity. The interior of a black hole and the moment of the Big Bang is where these two great theories collide. If we are living inside a black hole, then the very fabric of our universe is the product of physics we do not yet understand. The implications stretch into philosophy as well. The belief that the universe is all there is has been a constant in scientific thought since the Copernican revolution displaced Earth from the center of creation. But here, the Copernican principle is extended to the extreme. Not only are we not central within our universe itself may be one among countless others, each the interior of a black hole formed elsewhere. And then there is the question of inheritance. If universes are born inside black holes, could they inherit properties from their parent universes? Could the speed of light, the strength of gravity, or the values of fundamental constants be passed down through some cosmic mechanism? If so, the apparent fine-tuning of our universe for the existence of stars, planets, and life might be the result of a deeper evolutionary process, a kind of cosmic natural selection, in which universes that produce more black holes create more offspring universes. To accept this is to accept that our reality may be nested, generation within generation, each universe giving rise to others. The chain could stretch back without limit. There may be no ultimate origin, only an endless sequence of endings that are also beginnings. The scientific shock is not that this model is proven. It is that it is plausible enough to be considered seriously, consistent with both general relativity and certain quantum gravity theories. The boundaries it reveals are not those of space, but of knowledge. If we are inside a black hole, we cannot look beyond our own cosmic horizon. The outside is hidden from us not by distance, but by the very structure of spacetime. And yet, from within, our universe feels whole. The galaxies drift apart, The cosmic microwave background glows faintly from all directions, and the laws of physics appear universal. There is no hint in daily life that the stage on which we exist is enclosed by an unseen wall. The idea that such a wall exists, that we are contained inside something larger, forces us to reconsider the meaning of everything. If it is true, then the night sky is not the open expanse we imagine, but the interior of a vast cosmic chamber. Beyond its limits lies a place we can never reach, a place whose nature is as far beyond us as the universe is beyond the perspective of a single atom. And in that greater space, our universe is not exceptional. It is simply one among many, a bright bloom in a field of infinite creation. The deeper one follows this line of thought, the more the boundaries between what we know and what we can only imagine begin to blur. The hypothesis that our universe could be the interior of a black hole does not rest on whimsy alone. It grows from the mathematics of space-time, the strange geometries hidden in Einstein's field equations, and the clues embedded in our own cosmic history. In 1916, Carl Schwarzschild's solution to Einstein's equations described the space-time geometry around a perfectly spherical mass. It was simple, elegant, and startling. A structure where, beyond a certain radius, no path led back out into the universe. That radius would later be called the Schwarzschild radius, and it defined the event horizon. But the solution contained more than a static hole in space. When extended to its maximal form by Martin Kruskal and George Sikaris in the 1962nd, it revealed something richer, a mathematical bridge, an Einstein-Rosen bridge, connecting two separate regions of space-time. These diagrams were strange maps, showing how an event horizon could hide not just a singularity, but another universe entirely. In the Kruskal-Sikaris extension, the interior spacetime does not simply collapse into a point, it extends into another domain. In principle, that other region could be vast. From the perspective of anything inside, it could look like an entire universe, complete with its own space, time, and horizon. For decades, these were seen as mathematical curiosities, fragile under the weight of physical reality. In the real universe, black holes form from collapsing stars, not from the eternal, static solutions of idealized geometry. And yet, the mathematics refuse to go away. As physicists explored quantum gravity, the still elusive framework uniting relativity with quantum mechanics, the singularity at a black hole's core began to look less like an endpoint and more like a doorway. Loop quantum gravity, one contender in the search for a theory of everything, predicts that the collapse toward a singularity is halted at scales where space-time itself becomes quantized. In this view, the interior density reaches a maximum, then rebounds in what is sometimes called a bounce. On the inside, this rebound could appear as an expanding universe, a Big Bang without the infinite compression, emerging from the collapse of another space-time's matter. Cosmic inflation theory adds another layer. In our own universe's earliest moments, space expanded faster than light, smoothing out irregularities and explaining the remarkable uniformity of the cosmic microwave background. Inflationary physics describes conditions strikingly similar to what might exist just inside the horizon of a newborn black hole universe. Rapid expansion, high energy density, and the imprinting of quantum fluctuations across the fabric of space. These are features common to both scenarios. Observational cosmology offers subtle hints, though none are conclusive. The curvature of space, the distribution of galaxies on the largest scales, and the patterns in the CMB are all consistent with a universe that is finite yet unbounded. A description that could apply to the inside of a black hole. There is no direct sign that our cosmic horizon is an event horizon, but the mathematics allows for the possibility. The white hole concept deepens the analogy. A white hole is the time-reverse twin of a black hole. Instead of drawing matter in, it ejects it. In certain space-time solutions, the Big Bang behaves exactly like a white hole, spewing matter and energy into existence. If every black hole connects to a white hole in another space-time, then perhaps our own universe's origin was such an eruption. From the outside of our parent black hole, the moment we call the Big Bang would have appeared as a final flash of light and matter frozen at the horizon. Inside, it was the dawn of everything. This vision is difficult to test, and yet it fits comfortably within the strange logic of modern physics. It removes the singularity as a point of infinite density, an idea many physicists see as a sign that classical theory has reached its limit. It replaces it with a finite, if extreme, condition from which expansion begins. The transition from collapse to expansion becomes a bridge between two universes, a continuous thread in the fabric of a multiverse. The challenge lies in the barrier itself. The event horizon ensures that no information from outside our universe can reach us, and no signal from within can escape to confirm the hypothesis to any external observer. We can only work from the inside, studying the properties of our cosmos for indirect signs that we are enclosed. Supercomputer simulations of black hole formation hint at the complexity hidden beyond the horizon. Matter falling inward is not swallowed in a featureless void. It is compressed, heated, and twisted into patterns defined by space-time's curvature. In the models, as the collapse proceeds toward the Planck scale, where quantum effects dominate the classical picture, gives way to one in which space-time can transition to a new, expanding region. Physicists like Nikodym Popławski have attempted to map this transition using equations from Einstein-Cartan theory, which extends general relativity to include a property of matter called spin. In this framework, spin generates a repulsive force at extremely high densities, preventing a singularity from forming and driving the creation of a new spacetime. This torsion acts like a safeguard in nature's architecture, ensuring that collapse is never final but always transforms into expansion somewhere else. In this picture, every black hole becomes a cosmic seed. The matter and energy it consumes are not destroyed, but recycled into a new universe on the other side of the horizon. To observers in the parent universe, the black hole remains a region of darkness. To observers inside the child universe, it appears as an entire cosmos, possibly with different physical constants and dimensions. If our universe was born this way, then the constants we measure, the strength of gravity, the masses of fundamental particles, the rate of cosmic expansion, may be inherited traits. Just as biological offspring carry genetic information from their parents, universes might carry physical information from the black holes that birthed them. This speculation leads to the idea of cosmological natural selection. Universes that produce many black holes may give rise to more offspring, filling the multiverse with those best suited for black hole formation. In the laboratory of thought, this process could explain why our universe seems fine-tuned for the formation of stars and galaxies. Conditions that favor star formation also favor the creation of massive stars that will end their lives as black holes. If such black holes spawn new universes, then the cycle reinforces itself, selecting for universes like ours. Still, the deepest mysteries remain untouched. What lies beyond our horizon? What, if anything, came before the black hole that became our universe? Is there an ultimate origin to the chain of creation, or does it extend backward without end? These questions reach beyond the capacity of our current tools, lingering at the edge of science where mathematics shades into philosophy. And yet, the parallels between the inside of a black hole and the early universe are too striking to dismiss. The same equations that describe the bending of starlight around a black hole also describe the curvature of space in the moments after the Big Bang. The same concepts that predict an event horizon also define the cosmic horizon we see when we look to the limits of the observable universe. The boundary between them may be more than a coincidence. It may be the imprint of our origin. If that is true, then every night sky is not an open window into infinity, but a glimpse at the inner walls of a cosmic chamber. And every black hole we observe in that sky is not only an end, but perhaps the beginning of another universe, hidden from us yet unfolding its own galaxies, stars, and worlds. If the universe is the interior of a black hole, then it is not alone. The idea unfolds into something larger, stranger, and more intricate than a single origin. In this model, every black hole could be a cradle for a new cosmos. Each one a seed that falls inward from one reality, only to bloom in another. The chain is endless, branching and weaving through the fabric of existence. Our own universe might be just one bloom in an infinite field. From the outside of any black hole, its surface is an event horizon, still, silent, inescapable. From the inside, it could be a horizon of creation, the edge of a newborn cosmos, expanding at incredible speed. In our universe, there are countless black holes, from stellar mass remnants, only a few kilometers wide, to supermassive giants with masses billions of times that of the Sunday. If the hypothesis is correct, each of them could be the first chapter of an entire reality, hidden from us as completely as ours is hidden from whatever lies beyond. The notion of cosmic inheritance transforms the familiar puzzle of fine-tuning into something dynamic. Our universe appears to have physical constants, precisely set for the formation of stars, galaxies, and the complex chemistry that makes life possible. Traditionally, this has been treated as either a cosmic coincidence, the work of deeper unknown laws, or evidence for a multiverse in which countless variations exist. But if universes are born from black holes, their traits may not be random. In cosmological natural selection, proposed by Lee Smolin, universes that produce many black holes also produce many offspring universes. The parameters that govern physics, the strength of gravity, the charge of the electron, the mass of the proton may shift slightly with each generation. Over eons, universes that favor black hole production become more common, while those that do not fade away. This would explain why our universe is so prolific, with stars and massive stellar deaths. We live in a reality optimized through countless cycles for the creation of more realities. If this is true, then black holes are not cosmic waste bins, swallowing matter into oblivion. They are engines of renewal, taking the ashes of old stars and forging entirely new arenas for physics to play out. They are not the dead ends of the universe, but its reproductive organs. And in that sense, death and creation are no longer opposites, but the same act seen from different sides of the horizon. The hierarchy implied by this vision is staggering. Our universe could be a child of another, whose own parent was born in the depths of a different cosmos, stretching backward without a first cause. The line may have no beginning, no ultimate origin point, only an eternal network of creation and collapse, expansion and contraction. The familiar image of the universe as a single, isolated whole dissolves into a fractal of nested realities. In this perspective, the Big Bang loses its status as an absolute starting point. It becomes an event in a chain important to us, but not unique. The physics of our earliest moments may carry traces of the conditions inside the black hole that gave birth to us. The rapid expansion we call cosmic inflation may be the momentum of collapse transformed into outward growth. The homogeneity of the cosmic microwave background may be the echo of a parent universe's stability. Even the rate of our expansion driven today by what we call dark energy might be a legacy. If the constants we inherit determine not only how matter behaves, but how space itself stretches, then the very pace of our cosmic unfolding could be part of the reproductive blueprint. A universe that expands too slowly might collapse before producing many black holes. One that expands too quickly might disperse matter too thinly for stars to form. Our expansion rate is balanced between these extremes, perhaps not by accident, but by ancestry. This model raises a profound inversion. The ultimate purpose of a universe in physical terms might not be to sustain life, but to produce black holes. Life, in this sense, is incidental, a byproduct of the same conditions that favor massive stars and stellar death. And yet, in producing us, the universe has also produced beings capable of wondering about its origins, mapping its expansion, and imagining realities beyond its horizon. The more one contemplates this, the more the question changes. It is no longer simply, are we inside a black hole? It becomes, what kind of black hole are we in? What traits did we inherit? And what universes will be born from ours? If our own black holes give rise to new universes, they may inherit not only physical constants, but also the seeds of complexity that could eventually lead to observers like us. In that case, the cycle is not just physical, but informational. Patterns of structure, stability, and even habitability could propagate through generations of universes, as surely as DNA carries traits across generations of life. This is where the mystery deepens into the unknowable. We cannot reach the outside of our own horizon to confirm the existence of a parent universe. Nor can we look into the interiors of our black holes to watch new universes emerge. The barriers are not technological, they are written into the geometry of space-time itself. In this model, every universe is a self-contained room in an infinite labyrinth, with doors that open only one way. And yet, the logic is seductive. It transforms black holes from menacing voids into cosmic wombs. It connects the smallest scale of quantum mechanics to the largest scale of cosmology, uniting collapse and creation in a single process. It reframes our place in the cosmos. We are not at the end of a long chain of chance events, but part of a pattern that has played out countless times before and will play out countless times again. The hierarchy of universes may be infinite, but for us, it is also invisible. We are sealed in, our instruments blind to the outside. We can only infer, imagine, and build models. And yet, this may be enough. Physics has often revealed truths about places we cannot visit: the heart of a star, the center of the Earth, the first microseconds after the Big Bang. If the idea that we are inside a black hole is true, then perhaps the clues are already around us, woven into the geometry of our cosmos, waiting for the right theory to bring them into focus. And so the question lingers, heavier now with implication. Our universe may be one in an endless cascade, each reality born from the collapse of another. The black holes we see in our sky may be gateways to other skies, filled with other stars, waiting for their own observers to look up and wonder if they too are inside something larger. The deeper we descend into this question, the more it unfolds into a lattice of possible truths. The idea that our universe resides inside a black hole is not a single theory, but a convergence point, where several lines of thought meet. Each theory offers a different shape to the same vision. A universe nested inside a greater structure, its origins hidden beyond the reach of light. One of the clearest formulations comes from physicist Nikodem Popowski. In the early 2010 second, he explored the mathematics of Einstein's general relativity when merged with an older, lesser-known extension called Einstein-Cartan theory. This theory introduces the concept of space-time torsion, a twist in the fabric of reality that emerges when matter with intrinsic spin interacts with gravity. Under such conditions, the singularities predicted by general relativity may not exist as infinitely dense points. Instead, the collapse of a massive star halts at an extreme but finite density, triggering a rebound, a bounce. In Popowski's model, the bounce does not eject matter back into the same universe. It creates a new expanding region of space-time, a new universe. The event horizon seals it off from the parent universe, making two realms forever inaccessible to one another. From inside, this event looks like a Big Bang. From outside, it is seen as the silent formation of a black hole. In this view, every black hole may be the birthplace of a cosmos, and our own Big Bang could be the bounce from a black hole's collapse in a parent universe. Another pathway comes from loop quantum gravity. Unlike string theory, which tries to describe all particles as vibrations of one-dimensional strings. Loop quantum gravity focuses on quantizing space-time itself, breaking the fabric of reality into tiny, discrete loops, smaller than anything we can directly measure. In this framework, the infinite density of a singularity cannot occur. Instead, as the matter compresses, quantum gravitational effects create a repulsive force that grows stronger than gravity itself, forcing the collapse to reverse. The result is again a bounce, with the new expansion potentially forming a universe. Here, the bounce is not just a mathematical curiosity, it is a natural consequence of a quantum structure to space-time. The Big Bang is reimagined as a big bounce, and black holes become the engines of this cosmic recycling process. The old gives birth to the new, endlessly. Lee Smolin's cosmological natural selection shifts the focus from how universes are born to why they might have the properties they do. In Smolin's idea, the constants of physics, the gravitational constant, the mass of elementary particles, the cosmological constant, may vary slightly with each new universe born from a black hole. Universes with physical laws that favor the formation of stars, and thus black holes, will produce more offspring. Over countless generations, universes evolve toward configurations that maximize black hole production. This model reframes the fine-tuning problem. The conditions that make life possible are a side effect of conditions that make black holes plentiful. We are not here because the universe is tuned for us. We are here because the universe is tuned for black holes, and those same parameters happen to allow life. If this is correct, then every law of physics we observe, from the speed of light to the behavior of subatomic particles, may be an inheritance from a long line of cosmic ancestors. Then there is the holographic principle, born from the study of black hole thermodynamics and quantum information theory. In the 1972, physicists Jacob Bekenstein and Stephen Hawking revealed that black holes have entropy proportional to the area of their event horizon, not their volume. This suggested a startling idea. All the information contained in a region of space could be encoded on its boundary. Later, Gerard Hooft and Leonard Susskind extended this insight into a general principle: the physics within any region might be entirely described by information stored on a surrounding surface. If our universe is inside a black hole, then perhaps everything we experience, every galaxy, every atom, every thought, is encoded on the inner surface of a higher dimensional horizon. We may be living inside a hologram projected from that surface. The outside world would exist in a higher dimensional space, forever hidden, yet continuously shaping the physics we know. Some speculative extensions even imagine that faint traces of a parent universe might survive the transition. Subtle asymmetries in the cosmic microwave background, the oldest light in our universe, could be imprints from the geometry or energy conditions inside the black hole that birthed us. Certain patterns of polarization or temperature fluctuation, if ever observed, could hint that our Big Bang was not the start from nothing, but the continuation of a much older story. But every theory, however compelling, faces the same wall: the event horizon. It is not just a physical barrier, it is a causal one. Information cannot travel from beyond it into our universe. Any clue about the outside must be indirect, encoded in the properties of our own space-time, our own matter, our own light. This makes the question both scientifically treacherous and philosophically rich. And so, physicists turn to analogies and models. They simulate collapsing stars and expanding universes on supercomputers, watching for connections. They look for mathematical consistencies between black hole interiors and cosmological expansion. They probe quantum gravity for mechanisms that could replace singularities with new spacetimes. For some, the appeal is not just in solving a mystery, but in uniting the greatest puzzles of physics. Black holes are where gravity, quantum mechanics, and thermodynamics all meet, and where they currently resist full reconciliation. The Big Bang is another such meeting point. If both are, in fact, the same kind of event seen from different sides, then understanding one may illuminate the other. Even within the community of physicists, reactions to these ideas range from cautious curiosity to outright skepticism. The mathematics is elegant, but the lack of direct evidence leaves the theories vulnerable. Yet history reminds us that much of modern cosmology was once speculation. Dark matter, dark energy, even the expansion of the universe itself, were all invisible truths before the evidence arrived. The possibility that our universe is inside a black hole is more than a scientific question. It reshapes the emotional landscape of existence. It suggests that everything we have ever known is contained within something else's end, that our reality is both infinite in scope and finite in boundary. That when we look into the darkness of a black hole, we may be looking at a place where new universes are being born, just as ours once was. And if that is true, then the night sky changes meaning. Each black hole becomes a mystery twice over, a silent region in our universe, and perhaps a universe in its own right. A cradle sealed by gravity, carrying forward the chain of creation. If our universe is the interior of a black hole, then the truth of that claim must be written somewhere in the patterns of nature. But it will not reveal itself easily. The event horizon is not a wall we can breach, not even with light itself. The only way forward is through inference, reading the shadows, echoes, and distortions that the deeper structure of reality may leave behind. For scientists, the challenge is twofold. To imagine the tests that could separate ordinary cosmology from black hole cosmology, and to build instruments precise enough to carry them out. The most immediate tools lie in our telescopes. In April 2019, humanity saw for the first time the silhouette of a black hole, the glowing ring around the shadow of M87*, captured by the Event Horizon Telescope. It was not a single telescope, but an Earth-sized array, linking radio observatories across the globe into one synchronized eye. That image, and the later one of Sagittarius A, proved that we could resolve the very edge of an event horizon. Future iterations of the EHT, with more stations and greater sensitivity, could reveal subtle structure in the photon ring, the last orbit of light around a black hole, testing predictions from general relativity and quantum gravity alike. If the interior of a black hole is a universe, certain theoretical models predict that the dynamics at the horizon could differ in ways too small for current instruments to detect. But as resolution and sensitivity improve, we may be able to probe the nature of the horizon itself. Is it a perfect one-way membrane, or does it hold faint, scrambled imprints of what lies within? Beyond the silent image of a shadow, there is motion, and with it, gravitational waves. The LIGO and Virgo detectors, joined by CAGRA in Japan, have already caught the tremors of space-time from merging black holes. Each collision is a pure gravitational event, untainted by matter or light. In the waveform of those ripples, scientists search for the ringdown, the last vibrations of a newly formed black hole. If our black holes lead to new universes, perhaps the ringdown hides clues, tiny echoes, irregular decays, or deviations from Einstein's predictions. The future LISA mission, a space-based gravitational wave observatory, will listen to lower frequencies from the dance of supermassive black holes, opening a new register in the cosmic symphony. Yet the key to our origin may not be found in black holes themselves, but in the cosmic microwave background, the oldest light in our universe, released when the first atoms formed, nearly 380,000 years after the Big Bang. The CMB is our baby picture, a map of temperature fluctuations across the sky. The Planck satellite has given us its most detailed view, revealing patterns that match the predictions of inflationary cosmology. But certain anomalies remain. A curious cold spot, hemispherical asymmetries, alignments of temperature fluctuations. If our universe is the offspring of a black hole, could these be faint birthmarks from the parent? Some theorists suggest that the curvature topology, or even the statistical distribution of fluctuations might carry signatures of the geometry inside a black hole's interior. Future CMB missions with higher precision polarization mapping could search for these fingerprints. It is a delicate hunt. The signal, if it exists, would be buried in the faintest whispers of the oldest light. On another front, particle physics seeks answers in the smallest scales. The Large Hadron Collider smashes protons together at energies that briefly recreate conditions close to those of the early universe. In these collisions, researchers probe the limits of the Standard Model, searching for particles or behaviors predicted by quantum gravity theories. If space and time are quantized, if singularities are replaced by bounces, there may be subtle consequences for high-energy physics-minute deviations in scattering probabilities, unexpected resonances, or the presence of extra dimensions. Plans for future colliders, larger, more powerful than the LHC, are already on the drawing board. They may not detect a black hole directly, but they could test the mathematical frameworks that make black hole cosmology plausible. Each experiment narrows the space in which truth can hide. Even the oceans hide part of this search. Submerged detectors like IceCube in Antarctica and deep-sea neutrino observatories hunt for ghostly particles from the far reaches of space. Neutrinos pass almost untouched through matter, carrying information from environments light cannot escape. If the earliest moments of our universe, the inside of the black hole that birthed us, produced unique neutrino signatures, they may still be drifting through the cosmos, waiting to be caught. Some researchers are turning to artificial intelligence as a new lens. Feeding vast datasets of cosmic observations into learning algorithms, they search for patterns the human eye might overlook, correlations across different scales, anomalies in the large-scale structure of galaxies, or statistical outliers in black hole populations. If there is a hidden order shaped by a parent universe's physics, perhaps the imprint can be teased from the noise. Simulations, too, are a kind of instrument not of glass and metal, but of mathematics and silicon. Supercomputers now model the collapse of massive stars into black holes with increasing realism, tracking the curvature of space-time, the behavior of quantum fields, the interplay of gravity and thermodynamics. Some simulations have shown how certain collapse scenarios could naturally lead to an expanding interior with properties resembling our own cosmos. These virtual experiments are not proof, but they are maps of the possible, guiding observers toward the signatures worth chasing in the real sky. Still, every tool faces the same horizon. We can circle it. We can study the light that grazes it and the waves that ripple from it, but we cannot step across. If we truly live inside a black hole, the boundary that separates us from the outside is absolute. Our search becomes an exercise in reading the inside of a closed book, inferring the cover from the style of the pages. Perhaps this is the greatest constraint and also the greatest wonder. Science has always thrived at the edge of the knowable. Whether we stand on the rim of an atom or the lip of an event horizon, we face the same truth. The unknown is not an absence, but a horizon in its own right. It is there to be approached, measured, and imagined against. And so, we watch the skies, we listen to the tremors in space-time. We decode the oldest light. Each observation is another brushstroke in a picture that may, one day, reveal not just how our universe began, but where it truly sits in the hierarchy of creation. Until then, the possibility remains suspended like a star's last breath before collapse, that we are living inside the very thing we once thought marked the end of all things. In the stillness of night, when the city's dim and the sky stretches unbroken above, the stars seem timeless. But each point of light is a story in motion, some just beginning, some already gone, their endings racing toward us across aeons. Beyond them, invisible to any human eye, lie the great silences, the black holes. From the outside, they are prisons. Light cannot climb free. Time itself appears to halt at their threshold. Yet the mathematics tells another story, that from the inside the arrow of time may run forward again, carrying whatever fell across that boundary into an entirely new existence. What we call collapse may be, from another vantage, a moment of birth. If that is true, then our own universe is not an isolated beginning, but the continuation of something else's ending. Our galaxies may be the debris of a star, too massive to survive its own gravity. A star in a reality beyond our reach. Everything we see, every tree, every ocean, every thought, could be unfolding in the interior of an object that, to another universe, appears only as a dark, silent point. The idea is humbling, but it also reshapes the notion of permanence. Civilizations dream of legacy of monuments that will outlast the fall of empires. Yet if universes themselves are born and die within the life cycles of greater structures, then permanence is only a matter of scale. Our own black holes may already be swelling with new realities, each with their own stars, their own physics, their own questions about origins. In this view, creation is not a singular event, but a chain, without a beginning or end, each link both a cradle and a grave. The Big Bang becomes not the first word in the story, but the first word of this chapter. Before it, another story was written. After it, another will begin. It is a vision that deepens the meaning of the night sky. The black holes we watch from afar may be, in some ultimate sense, our children's seeds of universes that will grow beyond our knowing. And if those universes form their own black holes, they too will bear descendants, their own chains of creation spiraling outward in infinite recursion. The human mind struggles with infinities. We measure life in decades, civilizations in centuries, and the age of the cosmos in billions of years. But this model demands something more, a recognition that even billions may be only the passing of a season in a far older, far larger garden. If so, then our place is not at the center of existence, nor at its edge, but as a thread in an endless tapestry. Each thread may never see the whole pattern, yet the pattern exists because of them. And in that tapestry, black holes are not the ends of roads, but the knots where threads turn and weave in new directions. There is a quiet beauty in this, to think that the ultimate fate of our universe, whether in heat, death, collapse, or something stranger, could be the beginning of another's dawn. That somewhere, someday, a civilization may look up at their night sky, wondering at the dark, devouring points between the stars, never knowing that one of them is us. Perhaps they will build their own mathematics, their own telescopes, their own questions about whether they live inside a black hole. Perhaps they will reach the same precipice of knowledge we stand upon, now able to see the horizon, unable to cross it. They too will wonder what lies beyond, and they too may never know. This is the strange gift of such a perspective. Certainty dissolves, but meaning expands. We are not the final act of creation, nor are we the beginning. We are a bridge. Everything we build, every discovery, every question asked in earnest, becomes part of the heritage passed through the horizon to whatever follows. In this light, the great silences are no longer empty. They are full, not with answers, but with possibilities. And so, when the last star fades in our sky and the galaxies drift apart into the deep cold, it may not be the end at all. It may be the moment when the fabric of our cosmos tightens, curves, and blooms into something else. We will not see it, but in the chain of universes, sight is not required for connection. We are part of the lineage, simply by existing. And so the question remains, lingering beyond calculation and proof. If our universe is inside a black hole, then what is outside? Another universe? An infinite stack of them? Or something stranger? Beyond even the reach of thought? No telescope can yet answer. No equation is final. For now, the horizon holds its silence. But perhaps that is fitting. For every horizon, no matter how absolute, is also an invitation to imagine, to search, and to understand that even the greatest darkness may be the womb of light.